Black holes are extreme phenomena, and their stars are not any different. But how exactly do they compare? And which of these two mysterious elements is the greater evil? Join us in this exciting video as we reveal everything you need to know about black hole stars. To get a better understanding of black hole stars, we must, as a matter of necessity, discuss their origin and other elements that are closely tied to their existence first. Without a shadow of a doubt or fear of contradiction, black holes are the most qualified elements to be discussed in this realm. Black holes have been described by scientists as a void or area of space where gravitational force is extremely strong, such that nothing can pass through it. And when we say nothing, we mean even the superfast particles of light, which travel at an unbelievable speed of 299,792,498 meters per second. In case you don't know how lethal and outrageous this level of speed is, the Parker Solar Probe, which is on record as the fastest spacecraft ever built by humans, has a top speed of 163 kilometers per second. But how do black holes generate so much gravitational pull to trap objects at such speeds? Well, this phenomenon is caused by the large amount of mass that is squeezed into a tiny volume of space, making it one of the most significant and paradoxical phenomena in the entire universe. From observations, when a massive star, one with at least 8 times the mass of our Sun, reaches the end of its lifetime, it collapses in on itself. This process creates a concentrated area of mass, which is known as a stellar black hole. But admittedly, not all stars become black holes. Some of them expand into red giants at the end of their lifetime. However, for stars to have a large enough mass to become a star, their core begins to collapse. First, their innermost layers are dragged into the center, followed by the outer layers. But as soon as the initial collapse of the outer layers is completed, they return with a bang as a supernova explosion. At this point, all that is left of the star is the core, and if it possesses up to 3 solar masses or more, it can continuously compact to smaller and denser volumes. Consequently, the gravity and escape velocity increases rapidly until the core becomes a black hole. At this point, we need to introduce escape velocity, which is the minimum speed an object must travel at to escape the gravitational field of a planetary body or any other body at all. For Earth, the escape velocity is around 11.2 kilometers per second, which is equivalent to 40,000 kilometers per hour. In layman's language, this might sound like a lot, but on a cosmic scale, it's inconsequential, especially when compared to the escape velocity of black holes, which is well over 1 billion kilometers per hour. The biggest and most giant black holes are known as supermassive black holes. On average, they possess masses that equal to over 100 times that of our Sun. And according to scientists, every galaxy in the universe has one of such black holes at their center, all of which are believed to have formed during the early phases of the Big Bang. One shocking irony about black holes is that despite their enormous amount of matter that they gulp and extravagant gravitational pull, they are completely invisible. However, astronomers and scientists are able to observe them by monitoring the gravity on the stars and around the hole. Now that we've established the relationship between stars and black holes and their enormous size, we move on to the black hole stars themselves, which are otherwise known as quasi-stars. These stars have enormous mass and are even bigger than our Sun, which makes up 99% of our solar system's mass. In fact, in the real sense of things, our Sun is regarded as a yellow dwarf and cannot compare to supergiants and hypergiants like Quasi-stars. While our Sun measures thousands of miles in diameter, Quasi-stars stretches up to hundreds of millions of miles in breadth. In summary, the red orb is the largest star we've ever observed, yet it is small and dwarf-like compared to a quasi-star. These hypothetical and mysterious elements are so big, their size is almost beyond human comprehension. According to a report, the average quasi-star can inflate up to more than 7,000 times the size of our Sun, and the largest among the strange astrophysical objects can expand to a diameter of more than 6 billion miles. Aside from being many times bigger than the average star, quasi-stars are also different in the way they generate energy. Stars have come to generate energy by converting hydrogen into helium in a process called nuclear fusion. In contrast, quasi-stars generate energy through the black hole at their centre. For this process, the matter that enters the black hole is used as fuel to generate outgoing radiation, which in turn powers the quasi-star. This means the mass of the central black hole would continue to increase as the outer star expands. And this process could eventually lead to the creation of a supermassive black hole with a concentration of billions of solar masses at its core. Critically, our understanding of quasi-stars helps in some way to explain the formation of supermassive black holes. But ironically, our understanding of the supermassive black holes remains a mystery that we are still trying to solve. As a matter of fact, scientists don't exactly know how they came to be. For instance, one of the oldest supermassive black holes ever observed by astronomers was a quasar at a redshift of 7.085. And as we know, higher redshifts indicate objects that are farther away from us. And with such redshift value, we know that this quasar would have formed at least less than 1 billion years after our universe was created during the Big Bang. Over time, several scholars have put forward different theories to explain how supermassive black holes could have existed at such a time when most of the other celestial elements in existence today had not even been formed. But we've come to realize that each and every one of these theories have their flaws. One of the most touted ideas was that quasi-stars could have been created by the after effects of the collapse of the population 3 stars. For the records, these are stars that existed at the earliest periods of the universe. By our calculations, these stars would have been light and fine, and since heavy elements were not in existence at the time, these stars would most likely have been made completely of hydrogen and helium. Just like the modern-age quasi-stars, population stars were extremely massive, sometimes weighing up to thousands of solar masses. However, their enormous size automatically means they have a shorter lifespan than smaller or more stable stars. According to these ancient theories, the collapse of population 3 stars is believed to have formed black holes, which in turn laid the foundation for the formation of the modern-day supermassive black holes. But we can't be too sure, especially because population stars are all but a result of an unproven hypothesis, just like quasi-stars. However, we cannot neglect them due to their importance. For instance, galaxies are made from vast collections of dust and stars bounded together by gravity. And like other galaxies, our galaxy has a supermassive black hole, probably formed from a quasi-star at its centre. But admittedly, it's too far away to cause us any trouble. This gives us a fair idea of how big and gigantic our universe is. Ideally, based on its complexity, quasi-stars should be just as popular as black holes. But it is not. Probably because it is only still a hypothetical concept that is yet to be proven by hard facts. And admittedly, this is one of the factors that has limited our understanding of the star formation and gas collapse process within the universe. But as always, scientists are working round the clock and hopefully they will unravel all of these mysteries someday.